Yes, GFCI breakers can be backfed, but specific conditions must be met. Firstly, the breaker must be designed for backfeeding. Secondly, the load side of the breaker must be connected to the protected line that is being used to power the generator. Thirdly, the line side of the breaker must be connected to a known ground source. A 50 amps one-phase breaker is not the correct protection for a 10 kilowatt generator. The generator is rated for 10 kilowatts, which would require a 41.7 amps breaker for three-phase operation. Since only one phase is being utilized, the correct breaker size would be 13.9 amps. A two-pole GFCI is designed to protect against ground faults in single-phase circuits. It works by comparing the current flowing in the phase conductor to the current flowing in the neutral conductor. If there is a difference between the two currents, it indicates that current is leaking to ground and the GFCI trips. Applications for two-pole GFCIs include single-phase loads without a neutral connection, multi-wire branch circuits, and generators where only one phase is being used. Grouping the neutral conductor, the equipment grounding conductor, which is abbreviated as EGC, and the bonding jumper on the same bus is a common practice in electrical installations. This is done to ensure that all components are properly grounded and protected against electrical hazards. In the specific case of a generator, the neutral conductor is connected to the frame of the generator, establishing a common reference point for electrical potential. The EGC is connected to the frame of the generator and the electrical equipment, providing a path for fault currents. The bonding jumper is connected between the neutral bus and the EGC bus to ensure that the neutral and EGC systems are properly interconnected. Let's delve deeper into each of these points, starting with GFCI breakers and backfeeding. When considering backfeeding a GFCI breaker, it is crucial to verify that the specific breaker model is designed and approved for this type of application. Not all GFCI breakers are created equal, and attempting to backfeed one that is not designed for it could lead to improper operation or even damage to the breaker. The manufacturer's specifications and instructions should be consulted to confirm the breaker's suitability for backfeeding. Assuming the GFCI breaker is approved for backfeeding, the load side of the breaker must be connected to the protected line being used to power the generator. This means that the wires carrying the power from the generator should be connected to the terminals in the breaker that are normally used to feed the load. This ensures that the GFCI circuitry is monitoring the current flowing through the generator supplied circuit. The line side of the breaker, which is normally connected to the main power source, must be connected to a known ground source when backfeeding. This is essential for the GFCI to function correctly. The ground source provides a reference point for the GFCI to detect any leakage current to ground. Without a proper ground connection, the GFCI may not be able to detect ground faults and may not trip as intended. Now let's turn our attention to the appropriate breaker size for the generator. The generator is rated for 10 kilowatts. When operating in a three-phase configuration, the generator can deliver its full 10 kilowatt output across the three phases. In this scenario, a 41.7 amps breaker would be appropriate to protect the generator from overload. This calculation is based on the formula for calculating current in a three-phase circuit, which takes into account the voltage and power factor. However, in the situation described, only one phase of the generator is being used. This means that the generator's full output capacity is not being utilized. Instead, the single-phase load is drawing power from only one of the three phases. In this case, the appropriate breaker size would be 13.9 amps. This low breaker size is necessary to protect the single-phase circuit from overload. Using a 50 amps breaker, as was initially installed, would provide inadequate protection and could allow the circuit to be overloaded, potentially leading to overheating or even a fire. Now let's discuss the operation and applications of a two-pole GFCI. A two-pole GFCI is designed to protect against ground faults in single-phase circuits. It is commonly used in applications where there is no neutral conductor, such as with some 240 volts loads. The two-pole GFCI works by comparing the current flowing in the two conductors that supply the load. In a normal circuit, the current flowing in one conductor should be equal to the current flowing in the other conductor. If there is a difference between the two currents, it indicates that current is leaking to ground. This leakage current is known as a ground fault. When the two-pole GFCI detects a ground fault, it quickly trips, interrupting the flow of current and preventing an electrical shock. Two-pole GFCIs are commonly used in several applications. Firstly, they can be used to protect single-phase loads that do not have a neutral conductor. For example, some 240 volts appliances, such as water heaters or air conditioners, may not have a neutral connection. In these cases, a two-pole GFCI can be used to provide ground fault protection. Secondly, two-pole GFCIs can be used to protect multi-wire branch circuits. A multi-wire branch circuit is a type of circuit that shares a common neutral conductor between two or more hot conductors. These circuits are commonly used to save on wiring costs, but they can also be more susceptible to ground faults. A two-pole GFCI can be used to protect a multi-wire branch circuit by monitoring the current flowing in each of the hot conductors. Thirdly, two-pole GFCIs can be used with generators where only one phase is being used. In this scenario, the two-pole GFCI can provide ground fault protection for the single-phase load that is being powered by the generator. Finally, let's discuss the practice of grouping the neutral conductor, the equipment grounding conductor, and the bonding jumper on the same bus. This is a common practice in electrical installations, and it is done to ensure that all components are properly grounded and protected against electrical hazards. The neutral conductor is the conductor that carries current back to the source. The equipment grounding conductor is a safety conductor that provides a path for fault currents to flow back to the source, tripping a breaker or fuse and preventing electrical shock. The bonding jumper is a conductor that connects the neutral bus to the equipment grounding bus, ensuring that the two systems are properly interconnected. In the case of a generator, the neutral conductor is typically connected to the frame of the generator. This establishes a common reference point for electrical potential and helps to prevent voltage differences between the generator frame and the surrounding environment. The equipment grounding conductor is connected to the frame of the generator and to the electrical equipment that is being powered by the generator. This provides a path for fault currents to flow back to the generator, tripping a breaker or fuse and preventing electrical shock. The bonding jumper is connected between the neutral bus and the equipment grounding bus. This ensures that the neutral and equipment grounding systems are properly interconnected, providing a low impedance path for fault currents to flow. This low impedance path is essential for the effective operation of the ground fault protection system. In summary, understanding the correct application of GFCI breakers, proper generator breaker sizing, and grounding practices is crucial for ensuring electrical safety. By following these guidelines, you can help to prevent electrical shock and other hazards. Remember to always consult with a qualified electrician if you have any questions or concerns about electrical installations or repairs. It's important to emphasize the role of a qualified electrician in ensuring electrical safety. Electrical work can be dangerous, and it's essential to have the knowledge and experience to perform it safely and correctly. A qualified electrician can assess your specific needs, recommend the appropriate solutions, and perform the work in accordance with all applicable codes and regulations. They can also troubleshoot any problems that may arise and ensure that your electrical system is functioning properly. When choosing an electrician, be sure to check their credentials and experience. Ask for references and verify that they are licensed and insured. A reputable electrician will be happy to provide you with this information. In addition to hiring a qualified electrician, it's also important to take some basic safety precautions yourself. Always turn off the power before working on any electrical equipment. Use insulated tools and wear appropriate personal protective equipment, such as gloves and safety glasses. Never work on electrical equipment in wet conditions. If you are not comfortable working on electrical equipment, don't hesitate to call a qualified electrician. Your safety is always the top priority. Let's delve deeper into the grounding and bonding aspects, particularly in relation to generators. Grounding and bonding are critical safety measures that help to minimize the risk of electric shock and fire. Grounding provides a path for fault currents to flow back to the source, tripping a breaker or fuse and interrupting the flow of current. Bonding ensures that all metallic parts of an electrical system are at the same electrical potential, preventing voltage differences that could cause electric shock. In the context of a generator, grounding and bonding are particularly important because generators are often used in situations where a reliable ground connection may not be readily available. For example, generators may be used at construction sites, outdoor events, or during power outages. In these situations, it's essential to establish a proper ground connection for the generator to ensure safety. There are several ways to ground a generator. One common method is to use a grounding rod. A grounding rod is a metal rod that is driven into the earth and connected to the generator's grounding terminal. The grounding rod provides a direct connection to earth, allowing fault currents to flow back to the source. Another method of grounding a generator is to connect it to a grounded building structure. This can be done by connecting the generator's grounding terminal to a metal water pipe or other grounded metal component of the building. This method is only effective if the building's grounding system is properly installed and maintained. In addition to grounding, bonding is also important for generator safety. Bonding involves connecting all metallic parts of the generator and the equipment being powered by the generator together using bonding jumpers. This ensures that all metallic parts are at the same electrical potential, preventing voltage differences that could cause electric shock. Bonding jumpers should be sized appropriately for the size of the generator and the equipment being powered. They should also be installed in accordance with all applicable codes and regulations. It's important to note that the specific grounding and bonding requirements for generators may vary depending on the application and the local codes. Always consult with a qualified electrician to ensure that your generator is properly grounded and bonded. Now, let's elaborate further on the GFCI protection for different types of circuits, emphasizing the specific scenarios where they are most effective and the potential pitfalls to avoid. GFCI protection is a vital safety measure that helps to prevent electrical shock by detecting and interrupting ground faults. A ground fault occurs when current leaks from a circuit to ground, which can happen if a wire is damaged or if someone comes into contact with a live wire. GFCIs are designed to detect even small amounts of leakage current and trip quickly, interrupting the flow of current and preventing electrical shock. There are different types of GFCIs available, each designed for specific applications. Outlet GFCIs are designed to protect individual outlets and are commonly used in bathrooms, kitchens, and other areas where there is a risk of water exposure. Breaker GFCIs are designed to protect entire circuits and are installed in the electrical panel. Portable GFCIs are designed to be used with portable tools and equipment. When choosing a GFCI, it's important to select the appropriate type for the application. Outlet GFCIs are a good choice for protecting individual outlets in areas where there is a risk of water exposure. Breaker GFCIs are a good choice for protecting entire circuits, such as those that supply power to outdoor outlets or swimming pools. Portable GFCIs are a good choice for protecting portable tools and equipment, such as power drills and lawnmowers. It's also important to install GFCIs correctly. Outlet GFCIs should be installed in place of standard outlets and wired according to the manufacturer's instructions. Breaker GFCIs should be installed in the electrical panel and wired according to the manufacturer's instructions. Portable GFCIs should be plugged into a standard outlet and the tool or equipment being used should be plugged into the GFCI. There are some common pitfalls to avoid when using GFCIs. One common mistake is to assume that a GFCI will protect against all types of electrical shock. GFCIs are designed to protect against ground faults, but they will not protect against shock from contact with a live wire and a neutral wire. Another common mistake is to overload a GFCI circuit. GFCIs are designed to trip when they detect a ground fault, but they can also trip if the circuit is overloaded. It's important to make sure that the circuit is not overloaded before using a GFCI. Finally, it's important to test GFCIs regularly. GFCIs should be tested at least once a month to make sure that they are working properly. To test a GFCI, simply press the test button on the GFCI. The GFCI should trip and interrupt the flow of current. If the GFCI does not trip, it should be replaced. By understanding the different types of GFCIs, installing them correctly, and avoiding common pitfalls, you can help to prevent electrical shock and ensure your safety. Remember to always consult with a qualified electrician if you have any questions or concerns about GFCI protection. Finally, let's address the broader topic of electrical safety and the importance of adhering to the National Electrical Code, abbreviated NEC. Electrical safety is a critical concern for everyone, whether you are a homeowner, a contractor, or an electrician. Electricity can be dangerous, and it's essential to take the necessary precautions to prevent electrical shock, fire, and other hazards. The NEC is a comprehensive set of standards for electrical installations. It is developed and maintained by the National Fire Protection Association, abbreviated NFPA, and is widely adopted throughout the United States. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. Adhering to the NEC is essential for ensuring electrical safety. The NEC provides detailed requirements for electrical installations, helping to prevent electrical hazards and ensure that electrical systems are safe and reliable. The NEC is updated every 3 years to reflect the latest technological advancements and safety practices. It's important to stay up to date with the latest edition of the NEC and to follow its requirements carefully. In addition to adhering to the NEC, there are other steps you can take to improve electrical safety. Firstly, regularly inspect your electrical system for any signs of damage or wear. Look for frayed wires, cracked outlets, and loose connections. Secondly, avoid overloading circuits. Overloading circuits can cause overheating and increase the risk of fire. Thirdly, use ground fault circuit interrupters in areas where there is a risk of water exposure. Fourthly, never work on electrical equipment unless you are qualified to do so. Electrical work can be dangerous, and it's essential to have the knowledge and experience to perform it safely and correctly. Fifthly, always turn off the power before working on any electrical equipment. Sixthly, use insulated tools and wear appropriate personal protective equipment, such as gloves and safety glasses. Seventhly, never work on electrical equipment in wet conditions. Eighthly, if you are not comfortable working on electrical equipment, don't hesitate to call a qualified electrician. By following these guidelines and adhering to the NEC, you can help to prevent electrical shock, fire, and other hazards and ensure the safety of yourself and others. Electrical safety is everyone's responsibility, and it's essential to take it seriously.